Alright, so in this video we're going to be doing some final review for Calculus 3. Now this is probably going to be a two-parter. I'm probably going to make this part one of 2 videos, probably not 3. But the reason being is because if I was going to cram everything into this video, it would probably be like 3.5 hours long, and I know nobody really wants to sit through and cram all that in one night. So what I figured I could do is I'll split this up, and that way you could spend 2 nights just reviewing this material, not just cramming it all in one. In this video, we're going to be covering everything except for multiple integrals and vector calculus. Those are very big topics, and those are going to have their own separate video. Okay, so let's get right into what we're going to be doing in this video. Now, in this video, we are just going to be covering these first 3. Okay, so we're gonna first off we're gonna have 2 problems that are just finding the equations of lines and planes, and then we have a quadric surfaces problem as well. We're going to have some problems dealing with vector functions. There's going to be 2 of those, and then we're going to have 6 problems on partial derivatives. That's going to be 10 problems altogether. Now you may be wondering, okay, you might see the time length of this video and go, you're only doing 10 problems. Well, I'm going to be doing a pretty thorough explanation for each of these topics, because honestly, there's a lot of very diverse topics in Calculus 3, like, going from the equation of planes to Lagrange multipliers, right? So there's a lot of very different topics, and I want to make sure that I can hit on all of those and make sure that you understand them conceptually. Like, for example, when I was in Calculus 3 a few semesters ago, I did directional derivatives, I did gradients, I did Lagrange multipliers, but I never really understood what they meant. And I want to make sure that you understand what they mean, because then it's going to be, easier to understand what's going on when you're given a problem with those topics. Okay, so anyways, let's hop right into this, and we're going to start off with our first problem, which is asking us to find an equation for the plane that passes through the points. We have 1, 3, 2. We have point Q, which is 3, -1, 6, and we have point R, which is 5, 2, 0. Now, when we find the equation of a line, what are the 2 things that we need? Well, we need a point that's on that line, and we need the direction of that line, right? So I'll even write that down here. Okay, I'll write that in gray. So for a line, we need point and direction. But for a plane, we can't just have a direction, right? So that direction, if that's just pointing in the direction of the plane, there could be infinitely many lines which that you could draw from. So it's not very specific, and what will happen is you can also have infinitely many planes if you just specify one single direction. So that's not going to work out here. What we end up doing instead is having a normal vector. Okay, so now instead of that direction being parallel to the plane, so it's in the direction of the plane, it's perpendicular to it. Okay, so we just have a point in the plane, and we have a normal vector. Okay, and that's how we can define a single plane. All right, so the first thing that we're going to want to do, okay, we have the points. We just need to find the normal vector. Okay, so how are we going to find that normal vector? Well, we have some points, right? We can find 2 vectors that are in that plane, and if we take the cross product, we'll get the normal vector, right? So I'll even draw that out for you, just so you can get a visual if you're not already seeing that. Okay, so we find 2 vectors. Okay, let's say we find vector PQ. Okay, and we find vector PR. Okay, well, what we can do is take the cross product of these 2 vectors and get a vector that is normal to both these vectors, so it's normal to the plane. All right, so that's what we're going to attempt to do here. All right, let's start off and let's find our first vector, which we will do we'll do point R subtracted from point P. Okay? And we get just 5 minus 1 is 4, 2 minus 3 is -1, 0 minus 2 is -2. So we get our first vector. All right, this is a vector in the plane. Now let's get our second one. Let's take that point R again. Okay, you can do any points that you want. I'm just doing these because these are what I already have written down. We have 3, -1, 6. Okay, and if you subtract these out, 5 minus 3 is 2, 2 minus -1 is 3, and 0 minus 6 is -6. Okay. So now, all we're going to do is take the cross product, and then we have our normal vector. So, if we're going to take the cross product of these two vectors, we got to set up our matrix. Okay, so we have I hat, j hat, k hat. Okay, we have 4, -1, 2 as our first vector, -2. We have 2, 3, -6 as our second vector, and now we just take the cross, we just find the determinant rather. So we have I hat times, we have a -1 times -6 minus a -2 times 3. Okay, and that's your I hat. Then you have minus j hat times, it's going to be a 4 times -6 minus a -2 times 2. And then you have plus k hat times 4 times 3 minus a -1 times 2. All right, so simplifying that down, and I'm sure you guys probably skipped some steps if you tried this on your own beforehand. I'm just doing this all out for completeness sake. I won't drag on like this too much. We're going to have a 6 plus 6 here. We're going to have minus j hat times, there's a -24 plus 4, and then we have plus k hat times, this is a 12 plus 2. Okay, so our normal vector just ends up being 12i minus, not minus, it's actually going to be a plus 20 j hat, and then we're going to have plus 14 k hat. And we can also just simplify this down to make things easier for ourselves and make this 6 I hat plus 10 j hat plus 7 k hat. Not a big deal. I mean, it's the same thing. Okay, and we can say that this is equal to the normal vector. Okay, so now let's find a point. So we got to use one of the points, and the point that I want to use is going to be the first point here. I'm going to use point 132. Okay, so we have a normal vector and we have our point, which is 132, and now we just have to find the equation of the plane. Okay, now what is that equation of the plane? Well, the linear form of the plane is ax plus by plus cz equals d. And by the way, as a quick note, you may see that d on either side of the equation. Doesn't matter, not a big deal. Okay, some people, they're just defining d as, the opposite of what somebody else is. So not a big deal. Anyways, what's a, what's x, y, z, what's all that stuff? Well, we know that the normal vector has components a, b, c, and our point has our x, y, and z. Okay, so what about d though? Well, we need to find that. So we need d. Okay, so that's the whole point right now. And once we find d, we're going to be okay. All right, so let's plug everything in here. Well, first off, we have a is 6, right? So that's this guy right here. Okay, then we have x is 1, and we're going to go so on through the equation. So we have plus b is 10, y is 3, plus c is 7, z is 2, and that's equal to d. We get 6 plus 30 plus 14 equals d, and we get d is equal to 50. All right, so that's great. Now, all we have to do is finish our equation for that plane. So we're not going to plug in for the x, y, and z now. All we're going to do is plug in for a, b, c, and d, and we're done. All right, so let's get to that. We can rewrite this as 6x plus 10y plus 7z equals 50. And there you go. All right, so that is our first problem completed. Let's move on to the next. Okay, so the next problem is asking us to graph x squared over 4 plus y squared minus z squared over 4 equals 1. Now, I'm going to get rid of this line. I don't like this line at all. Oh, well, I kind of got rid of it. Never mind. All right, well, listen. Here's the deal about this graphing problem, okay? Now, when I looked at these problems when I was in Calc 3 and earlier on, I kind of just brushed them off. Didn't really care about them. Kind of just, gave minimal effort. But I didn't realize how important these questions are. And, these ended up being kind of the bane of my existence when I was in Calc 3, because the thing is, these are extremely important for triple integrals, just visualizing what's going on if you're given a surface like this, or something of the sort. If you're given a surface like that, double integrals, different things like that. So just understanding what you're looking at is very important. Vector calculus, different things like that. So if you don't understand what this looks like, something like that, those triple integral problems, they're going to become really, really hard. So that's why I want to make sure I go over graphing at least one of these quadric surfaces. Okay, so let's examine this. Okay, so to try to figure out what we're kind of going to be looking at. Now, if you haven't reviewed your quadric surfaces before watching this video, which is understandable, this is actually really easy to see. And the reason why I'm saying that is because this piece right here, what is that? What would this become? If you just got rid of this, and you just have like this and this piece, this is an ellipse, right? So this is an ellipse. Okay, and now that I have to get rid of those crosses, okay, and rewrite ellipse, what would the other two pieces? So if we had like the y squared and the minus z squared over 4, and we got rid of the x squared over 4, what is that piece? Well, that's a hyperbola, right? So basically what we see now is that our quadric surface is going to consist of ellipses and hyperbolas. Okay, and all we have to do to kind of visualize this is use traces. And if you end up with a quadric surface in any kind of these integral problems, vector calc problems, just traces are going to be your best friend, just to visualize what's going on. Okay, so for these traces, what I want to do, and first off, before we get into that, I'm actually going to set up my axes. Okay, and there we go. We have x, y, and z. And I bet you guys wish you could do this on the final, right? Have perfectly straight axes. And yeah, anyways, our first trace is going to be on x equals 0, okay? Or actually, let's do when z equals 0. So when z equals 0, because this is going to be the easiest case now that I look at it, we get x squared over 4 plus y squared equals 1. Okay, so what is this? Well, remember we said before, this is an ellipse. Okay, this is an ellipse. So we'll just graph it as such. Now, if you're confused, and this is something I would probably be confused with, if you're confused with what does this over 4 actually do, just set y equal to 0 Okay, because then you're like, if you have a circle in the xy plane, and that's an awful circle, I know, but if you set y equal to 0, you're looking at either this point or this point, so you can tell how far that ellipse is shifted over on the x-axis now. Okay, that's the idea. That's why I'm saying set y equal to 0. So you're kind of doing a trace of a trace. All right, so if you set y equal to 0, you just get x squared over 4 equals 1. So x is going to equal plus or minus 2. So that kind of tells you that the x part is going to be longer than the y part. So we're going to have something like this. All right, so that's your z equals 0 trace. Okay, so next up, let's look at when, and honestly, it's going to be really not fun here to do, setting z equal to multiple things. So what I'm just going to do is set y equal to 0 next. So if we set y equal to 0, we get x squared over 4 minus z squared over 4 equals 1, and this is just a hyperbola. Okay, so we know that between or that if we just have our graph on the xz axis, it's just going to be a hyperbola. So we'll have a hyperbola right here, and we'll have one in the back right here. All right, and excuse the drawing. I'm not the best artist in the world if you haven't already figured that one out. But anyways, yeah, so that's our y equals 0 trace. And then we're just going to do our x equals 0 trace, and I'll do that down here. And when x equals 0, this equation up here is just going to become y squared minus z squared over 4 equals 1. Another hyperbola. So we can just see that that would come in the back here, and we'd have like 1 coming down here, but that looks really gross now, so I'm just going to get rid of these. And but you understand like what it looks like now, so I'm just going to erase those for just like, since it's going to be easier to look at it. And I'm going to try to draw this. Not bad. Okay. Could use some work. And good. All right, yep, that's as good as it's gonna get, guys. So that's all I can do. Now, you may be wondering, how do I know if it's a one-sheeted hyperboloid versus a two-sheeted hyperboloid? Now, you can figure this out from traces, but it may just be easier to remember that a one-sheeted hyperboloid is when you have 1 minus in the equation, and a two-sheeted hyperboloid is when you have 2 minuses, right? So 1 sheet, 1 minus, 2 sheet, 2 minuses, okay? That's how I would remember it, just because it's quick and simple. That's not too hard to remember, 1 and 1, 2 and 2. But yeah, anyways, let's move on to our next problem. And this will kind of be the last of our graphing problems. This is going to be with vector functions now, since we are in the orange section. Okay, and we are being asked to sketch and find the domain of the vector equation r of t, this should have a arrow here, equals the vector we have 3t and 2 minus t squared. Okay, now go ahead and try this on your own if you feel comfortable with it. If you don't, I'll go through it again, but it is good. It is really good to just try these problems on your own, and maybe you are more familiar with vector equations, and if so, yeah, then definitely go through with this. But I just wanted to offer that up. So if we have our x, y, and z axes, all right, all we have to do from this point on, honestly, is just see how each individual parameter is behaving. So, for instance, since 3 is in our x entry, we just have x equals 3. Okay, this is something that's constant. So this entire curve is going to be happening where x equals 3. Okay, if you have a constant like that in a vector equation, it's really, really nice. Okay, so we go 1, 2, 3. Okay, over in the x direction. So everything that is going to be happening for our graph is going to be happening on this shifted YZ plane. Okay, so now let's look at our other parameters. So we have y equals t, and we have z equals 2 minus t squared. Okay, so y is just increasing by t. Now, if y is t, okay, then we can just plug that into the z equation, honestly, and then we have, since we're only dealing with something on the yz plane here, we'll just have an equation with of z with respect to y, which, you know, that'll work out pretty well, especially since, you know, we already have y equal to t. So if we do that, we combine these two equations here, we get z equals 2 minus y squared. What does that mean? Well, we're just going to end up with a really nice parabola here, and it's just going to look something like this. Okay, and not going to include that arrow, actually. Let me redraw that. Nice. Okay, because the last thing that we're going to have to do is draw some arrows to denote the direction of the vector function. Okay, so try to get that right now. If you haven't been able to get this so far, just because you looked at this problem and you were like, what do we do? Because that's exactly what I would have looked at it with before I reviewed this, honestly. So how are we going to tell what direction it's moving in? Looking at this, all I would do is, okay, y is equal to t. So as y increases, t is increasing. So that gives it right away. Y increases in this direction. So this parabola is just moving in this direction. Okay, that's that. All right, and then we have number 4. We're going to find the unit tangent and unit normal vectors. We're going to find the curvature at t equals 2 and the arc length from t equals 0 to t equals 2 for the vector function r of t equals t 3 cosine t 3 sine t. I have all the formulas that you're going to need right here. I'm not sure if you'd be given those on a final exam. I assume no, but if you're given like a sheet or something, if you can walk in with a piece of paper. These are definitely formulas you want to put on there. And so let's kind of just get on with this. So if I copy this equation, okay, if I copy this equation down here, we can just start off by finding our unit tangent vector, right? That's the first guy we got to accomplish. Okay, the unit tangent vector is just equal to r prime over the magnitude of r prime. So the first thing that we're going to have to do is find r prime. Okay, and how do we take a derivative of a vector function? Well, all we have to do is just take a derivative of each component, right? That seems pretty intuitive. We just, it doesn't matter that they're all separated. We just take a derivative separately. Okay, so r prime of t, the derivative of t is 1. The derivative of 3 cosine t is going to be negative 3 sine t. And the derivative of 3 sine t is going to be 3 cosine t. All right, great. We have r prime of t. Now we have to find the magnitude of r prime of t. How do we find the magnitude of a vector function? Well, all we have to do is take the square root of the sum of the squares. Okay, so we take the square root of the sum of the squares of these guys right here. So we have 1 squared plus a negative 3 sine of t squared plus 3 cosine of t, and this whole thing is also getting squared. Okay, so we get the magnitude of r prime of t equals, now this is equal to the square root of 1 plus 9 sine squared t plus 9 cosine squared t. All right, and now what do we do? Well, we know we have a sine squared, a cosine squared. Let's use that Pythagorean identity and just get that over with, and then we'll just have a really nice radical. So we get the magnitude of r prime of t is equal to the square root of, I'll just go the extra step so everybody is on the same page here. We can take a 9 out of these two terms and get a sine squared t plus cosine squared t. And that gives us square root of 1 plus 9, which is 10. Okay, so that is r prime of t. And we already have, or sorry, that's the magnitude of r prime of t, which means it's the length of r prime of t, just in case anybody was confused on what magnitude means. I remember our physics teacher always had, in my high school physics teacher, always had a sign up in his room that said magnitude means size or amount. Okay, so I may be a little privileged understanding what magnitude meant at a younger age. So anyways, enough of that. We get that t prime of, not t prime, we get that the unit tangent vector as a function of time is going to equal, we have this r prime of t this guy right here. So let me get, this was inefficient. I'll use this guy. And I'm going to divide by the square root of 10. Okay, and we get 1 over square root of 10, negative 3 over square root of 10 sine t. And since I don't have enough room, let's move this down here and finish down here, because this is going to be 3 over rad 10 cosine t. All right, so if that is our finished unit tangent vector, then what is the next thing that we have to find? Well, it is the unit normal vector. So how do we find that unit normal vector? Well, we have to use this equation over here. We have we have to use that unit tangent vector. We take a derivative of it, and we put that over the magnitude of that unit tangent vector. Okay, so the first step is to find t prime of t. All right, and t prime of t is going to be, well, first off, the derivative of 1 over the square root of 10 is going to be 0. And then we have the derivative of negative 3 sine t over rad 10. That's going to be negative 3 over rad 10 cosine t. And then we have the derivative of 3 over rad 10 cosine t, which is just going to be negative 3 over rad 10 sine t. All right, we're going to put that over the magnitude of t prime of t. Square root of the sum of the squares, we have 0 squared plus a negative 3 over rad 10 cosine of t squared plus a negative 3 over rad 10 sine of t squared. This is now equal to, well, we can pull out the this is actually just going to be 9 over 10, and we'll pull that out and just have a cosine squared t plus sine squared t on the inside. So we get that the magnitude is equal to 3 over rad 10. Okay, so that's the magnitude. All right, so now all we have to do is put these things over each other. So we have that the unit normal vector is equal to that vector 0, negative 3 over rad 10 cosine t, negative 3 over rad 10 sine of t, and that's going to be all over 3 over rad 10. All right, so now you see that we're going to get some really nice cancellations here, and we will wind up with a nice unit normal vector that is just going to be 0, negative cosine t, and negative sine of t. All right, that right there is your unit normal vector. Okay, so we have 2 out of the 4 things that we need to find. Now we just got to move on to curvature, and we also have to find, what was the other thing we have to find? We have to find the arc length and the curvature. Okay, so the first thing we're going to find is the curvature. Okay, we need to find the curvature at t equals 2. The equation for the curvature is the magnitude of t prime of t over the magnitude of r prime of t. Okay, and remember we're finding the curvature at t equals 2. Okay, so curvature of t equals the magnitude of t prime of t over the magnitude of r prime of t. Now, what was the magnitude of t prime of t? It was this quantity right here, right? That 3 over rad 10. So we'll put that right over here, 3 over rad 10. And then what was the magnitude of r prime of t? We've already found these things, right? So it's just a plug and chug from here. The magnitude of r prime of t was rad 10. So we're going to put that down here. And we're just going to wind up, these rad 10s are going to get multiplied together. Okay, don't think that they get canceled out because this bottom rad 10 is not in the denominator of the denominator. So anyways, we get 3/10. So that is the curvature. And that's not even, that's going to be the curvature everywhere. That's not just the curvature at t equals 2. That's the curvature everywhere because that thing wasn't even dependent on t, right? The magnitudes didn't have any variables in them that stayed through, okay? And the reason for that being, by the way, is because we had the only things we had that would have contributed is like the cosine t and the sine t, and those went away with that trig identity that we used. So that's why we don't have any variables in the curvature. Last thing we got to find here is the arc length, and then I'll let you guys take a break. A 5-minute break, preferably. That's probably going to be best for y'all. That's what I would do at least. We got to find the arc length from t equals 0 to t equals 2. And we got to use this formula right here. Okay? The arc length equals the integral from a to b of r prime of t dt. And that's the magnitude of that. So I'm going to copy this. Okay, and you guys can jot that down real quick. That's going to be the formula that we're about to use. Okay? We are going to go bam, bam. Okay. Yeah, so we're taking the integral from 0 to 2. What is that magnitude of r prime of t? That the magnitude of r prime of t is just rad 10. So we have rad 10 dt. Okay, so when we integrate here, we get t rad 10 evaluated from 0 to 2, and we just get 2 rad 10 is our arc length from 0 to 2. Okay, so that's kind of like all the intro stuff that that's all the problems I'm going to do on the intro stuff that we kind of did before partial derivatives. Okay, because your final is probably going to be a lot more focused on partial derivatives and multiple integrals and vector calculus. At least mine almost didn't even touch on anything except for vector calculus. It touched on a little bit of like Lagrange multipliers and max and mins and stuff like that, but really it was a lot of vector calculus. So I'm not going to spend too much time on these like earlier problems that you learn in like the earlier times of calculus 3. Okay, so moving on, we're going to get right into some partial derivative stuff here. All right, so for number 5, we want to find all the second partial derivatives for the function f of x and y equals sine of x squared minus y squared. Okay, so we're finding the second partial derivatives. Okay, so the first thing that we'll have to do to get to this goal is to find the partial with respect to x and the partial with respect to y. Okay, so just the first partial derivatives. Now, how do we take a partial derivative? And actually, before we even talk about that, what is a partial derivative? Like, what is it actually telling us, right? A lot of people learn partial derivatives, but they don't know what it means, okay? If you're taking a partial derivative, let's say you have some surface, Okay, some surface in 3 dimensions. Okay, just picture it. Okay, and you're taking a partial derivative with respect to x. All you're doing is finding the slope in the x direction, in a certain direction, right? The x direction for any point that you're at on that surface. You're able to find the slope in the x direction. If you're finding a partial derivative with respect to y, you're finding the slope in the y direction, okay, because there's infinite many directions on the surface. You're finding it in the y direction at any point. Okay, when we get into directional derivatives, it's a little bit different. Okay, so then it's any direction. But anyways, for now, those are partial derivatives. So we're finding the slope in the x direction for this surface that we have here. Okay, we have the partial derivative with respect to x here, where we know that the inside of this is just going to change, or sorry, the outside of this is just going to change to cosine of x squared minus y squared. And the derivative of the inside with respect to x, so the y squared goes away, we just have a 2x. So I can actually just move that out front. And we have 2x cosine of x squared minus y squared. Now for the partial with respect to y, we have, again, we're going to have cosine of x squared minus y squared, but the derivative of the inside is now negative 2y. Okay? Okay, and that's the whole thing with partial derivatives, right? If you're taking a partial with respect to x, you're treating y as a constant. So when we were taking the derivative of that inside with x squared minus y squared, the y's just treated like a constant. So it's like x squared plus 2. The 2 goes away, right? Doesn't matter. Worthless. Okay, so that's the first derivatives. Now we got to find the second derivatives, which, if you remember, are fxx, fxy, fyx, and fyy. So first off, for the partial derivative, the second partial derivative, actually, I'm not really sure how to say this. Let's just go fxx. All right. So to find that, we just take another derivative of this with respect to x, and what that is going to be is some product rule. So first, we're going to start off by taking the derivative of this 2x and dragging along the cosine, so we get a 2 cosine of x squared minus y squared. And then we're going to have the derivative of this cosine of x squared minus y squared times 2x. So the derivative of cosine of x squared minus y squared is going to be negative 2x sine of x squared minus y squared, right? The negative comes from the cosine converting to a sine. And we're going to multiply that by the 2x that straggles along. So simplifying that, we get 2 cosine of x squared minus y squared minus 4x squared sine of x squared minus y squared. All right, that's your partial derivative, but your second partial derivative of x. Now for the partial derivative, the second partial derivative of y, what we are going to do is just take another partial with respect to y of fy. So we take a derivative of cosine of, actually no, let's do that. Let's keep the consistency here. We'll take a derivative of negative 2y first, and we'll get a negative 2 times cosine of x squared minus y squared. Okay, and we're going to add on the derivative of cosine of x squared minus y squared, which is going to be, first off, we'll have a negative 2y, which is the derivative of the inside, times negative sine of x squared minus y squared, and then we have it all multiplied by a negative 2y. We have 3 negatives here, 1 here, here, and here. Okay, and so that is going to give us, when we simplify this, we get negative 2 cosine of x squared minus y squared minus a 4y squared sine of x squared minus y squared. And that is FYY. Now for fxy, all we have to do is take a partial of fx, this guy over here, with respect to y. Okay, so all that's going to happen is, since this, we don't have to do product rule because this 2x gets treated like a constant, and what we're just going to have is 2x times the derivative of negative y squared, the inside function, is negative 2y. So I'll bring that out, and then we'll convert this whole cosine of x squared minus y squared to negative sine of x squared minus y squared. So we get our fxy is equal to negative 4xy. And actually, since there's two negatives here, we're just going to make this a positive. So we'll have 4xy sine of x squared minus y squared. All right. Now, for the last partial derivative, fyx, we actually already have it. And, well, how do we already have it? Well, there's this thing called, well, I'm not really sure. I hope I don't butcher this name too hard, but Clairaut's theorem. Okay? And I'll write that so you can all see exactly what I'm talking about, and maybe the name, looking at it, will jog your memory a little bit more than hearing me say it. Clairaut's theorem is that fxy equals fyx. So sure enough, if we took a partial derivative of fy with respect to x, we would get the same thing. But we don't have to do that. All work because we can just cite Clairaut's theorem and get that fyx equals fxy. And there you go. Okay? And you can say via Clairaut's theorem, right? So I would make sure to note that, because you don't want to get a point taken off because you didn't state a theorem or something like that. So honestly, I would just write it down. Rather be safe than sorry. So for number 6, we want to find the differential of the function w equals xy squared cosine z. Now, what I want you to understand about differentials, okay, because while this was a small topic in Calc 3, it was, it was covered with tangent planes, approximations, things like that. So, approximating something, this is a lot of applications in like physics, things like that. So, and probably chemistry as well. I don't know too much in the chemistry field, so I'm a physics major myself. So, it's something to definitely go over. It's it's a good concept that you can take from Calc 3. So I really want to go over differentials here. Now, the thing about differentials, okay, this is something that should be actually familiar to you because it kind of is like a U sub. In a way, the formula makes sense because let's just take x's, okay? If you have w equals, if you make a U sub, let's say instead of w we write u equals 2x, then du equals 2 dx, right? How did we find du? Well, it was equal to the derivative with respect to x of 2x, and then we add a dx on the end. Okay? That's what this thing is saying. It's saying that d, instead of every time you see a w, just say a u, du equals partial, and we do partials now because we have multiple variables, partial u over partial x, and then you have the dx on the end. So that's where all that is coming from, and that should make sense. But now we're kind of adding on those extra variables. So what happens to the differential when you do certain things like this, right? So that's the whole idea of what you guys kind of covered with differentials. Okay, let's get into the problem. This should be a fairly simplistic problem. I just wanted to make sure I go over it because this should be a good takeaway from Calc 3, I think. And yeah, let's just find the partial derivatives. We have partial w over partial x equals, well, this just is, the y squared cosine z is a constant and the x goes away, so you just have y squared cosine z partial w partial y equals this y squared becomes a 2y, so you have 2xy cosine z. And lastly, you have partial w partial z, which gives you cosine z becomes a negative sine z, so you get negative x squared, no, sorry, negative xy squared sine of z. There you go. Now put it all together, get the partial, or sorry, get the differential of w. So partial w partial x is y squared cosine z. And we put a dx on the end. Plus 2xy cosine z dy. Plus, not plus, we're going to have a minus. Not 2, don't know where that came from. What am I doing? Xy squared sine of z. And that right there is your differential. Again, not too rigorous. I just wanted to go over, what a differential is because, like I said, it has a lot of applications later on. So, I wanted to make sure everybody is okay with that concept. Moving on to number 7, we are asked to derive the second partial derivative with respect to t for the function below. We have z as a function of r and theta, and these r and thetas have individual functions themselves with respect to other variables. So r is a function g with respect to s and t. Theta is a function h with respect to s and t. Okay, so now we have to use some kind of rule. What rule is that? Well, that's chain rule. Okay, now chain rule is pretty easy for first derivatives. Okay, but then second derivatives it might get a little more complex. So the derivation is going to be a little bit tougher. Okay, so let's start off with the first derivative. Okay, so for chain rule, we are going to set up the first derivative. Now the first derivative is going to be dz over dt. Okay, so this guy is equal to, first off, we have z as a function of r and theta. Okay, so r is a function of s and t. So to extract the t, what we have to do is first we have to go through this r, and we also have to go through theta. So our terms, we're going to have dz over dr. So we're going to take a partial with respect to r. Okay, and then for the r equation, we're going to take a partial with respect to t. And you see the dr's cancel out, and we just get dz over dt, right? So that works out. And then we do the same thing with the theta equation. So we take a partial derivative with respect to theta, and that's not added. Then we have d theta over dt. And there you go. Okay, so that's chain rule for the first derivative, right? That's pretty simple. That's, kind of intuitive, right? It makes sense. Okay, and also another thing to remember is that these are all going to have the curly d's, okay, because they're partial derivatives. Okay, they're when you're having a function of multiple variables. Okay, so you have to have the curly d's when you take a derivative. Okay, because you're only going to be taking a derivative with respect to one of those multiple variables. Okay, that's the chain rule for the first derivative. Now we have to move on to the second derivative, which is going to get a little more complex. So what we're going to have to do is take a derivative of on both of these sides. Okay, so we're going to take a partial derivative with respect to time of each side. Okay, so we can go through with that. We have d over dt of this huge thing, and I'm just going to copy this below. Okay, so in taking a partial with respect to time on both sides, we have, the d squared z over dt squared Okay, and how are we taking a partial with respect to t of this huge mess that we have going on the right hand side? What we're going to have to do is use some product rule here. Okay, so the reason why is, first off, these are two separate terms. This thing and this thing are two separate terms. Okay, so it's kind of like having like 2x plus 2 and taking a derivative with respect to x. Okay, that's just 2 plus 0, right? So it's 2. You can take the derivative separately of each term. But what I'm talking about here, but from using product rules, we have to use product rule inside here because we have two things being multiplied together. Okay? So we're going to have to use product rule here and product rule here. So we have two cases of product rule to deal with. Okay? So if we're trying to use product rule for the first pair, okay, let's use product rule for this piece right here. What we have to do first, let's take a partial derivative with respect to time of dz dr. Okay, so we'll do partial of dz dr. And then we're going to have to multiply dr dt, and we don't take a derivative of that. Okay, then we're going to add that to, we're going to do the opposite. We're going to take a partial derivative with respect to time of dr dt, and we're going to leave dz dr alone. Okay, and then since we did the first piece, now we're just going to add on to the second piece, the dz d theta dt. We're going to take a derivative with respect to time of dz d theta. Okay, and then we're going to multiply that by d theta dt, which we're going to leave alone. And then we're going to add that to the partial with respect to time of d theta dt. And we're going to multiply that by dz d theta, which we left alone. Okay? And this whole thing is your second partial derivative with respect to time. Okay? So you have to do quite a few things to actually get through to, you know, that time variable. So it is a little, or sure, to that t variable, and I believe I just referred to that as time throughout the whole problem. I don't know, but you understood what I meant there. Anyways, yeah. So chain rule can be really, really messy, especially with this. If I gave you all like the functions and everything, and I like real functions, and I didn't just make this like a general problem, this would be really, really messy to go and compute all of these different things. And yeah, I wasn't gonna do that to y'all. So anyways, that's how you work with chain rule. Okay, so the whole purpose of this problem was to get you to really understand how chain rule works, okay, and how we can find the second derivative with chain rule. Okay, we're about to get into like max and mins, Lagrange multipliers, and like some kind of and some gradient stuff as well. So if you want to take a break before we get into that, feel free. Take a 5-minute break, quick. Just kind of go over everything that we did. It was not the worst stuff in the world. Okay, so hopefully that all makes sense to you. So for number 8, we want to find the maximum rate of change of f at the given point and the direction at which it occurs. Our function is of two variables, x and y, and it's sine xy, and our point is 1, 0. So what we're trying to find the maximum rate of change of f. Okay, what are we looking for then? So what's that value called? It's the gradient. Okay, the gradient. So when I was in Calc 3, I would have been like, okay, why is the gradient the maximum rate of change, right? I was very confused as to why that is. So I want to explain that to you so you actually understand it, right? And that's all going to start out with partial derivatives, okay? I talked about what partial derivatives were earlier when we were covering it. A partial derivative with respect to x is the slope in the x direction at any point on a surface. The partial derivative with respect to y is the same thing, just the slope in the y direction at any point on the surface. Okay, A directional derivative, which gets covered with gradients, is the slope in any direction that you want, but you have to specify it with a unit vector. Okay, so you can't just find the slope in every single direction. You have to use a unit vector. Okay, so you only get to find the slope in a single direction. All right, so now that you understand directional derivatives, we have to use an equation that we know to figure out what the meaning of a gradient is. Okay, we know that the directional derivative of f equals del f, so the gradient of f dot u. Okay, so since this is an equation that we know, and if you want to understand why we're able to do this equation, you can look in your textbook or something like that. I don't want to spend too much time on this, but when you take the dot product of two things, you can just have the magnitude of those things times cosine theta, right? So a dot b equals ab cosine theta. So we can rewrite this as the magnitude of del f. Del f is a vector. It usually doesn't have a vector sign over it when I see it, so I think it's kind of just implied, but it's equal to that. So when will this directional derivative be a maximum? Well, the unit vector, the magnitude of the unit vector is always going to be 1. Okay? And cosine theta, what's the max that cosine theta can be? Well, 1. Okay? So at the max, the max slope of the directional derivative of f is equal to the magnitude of the gradient vector. Okay? So the direction of the steepest slope, right, is the gradient vector, and the magnitude of the gradient vector is the value of the steepest slope, right? So it's telling you what the steepest slope is from that point. Okay, that's why though. Okay, because we know we have that equation for the directional derivative. If we're trying to find the max, what's the maximum value that directional derivative could be? It's going to be the point where the angle between that unit vector and the directional derivative are the same, meaning that the direction you're going in is the direction of the gradient vector. Okay, because if they're parallel, then you end up with cosine of 0, right? So there's 0 degrees between those two angles, so that's 1. All right, so your unit vector, right, your direction of the steepest slope is the direction of the gradient vector. That's the whole point I'm getting at. That's why the gradient vector is the direction of the steepest slope. All right, so if you understand that, now we can kind of begin this problem. We want to find the maximum rate of change at f. I'll repeat the problem. We want to find the maximum rate of change of f, so we want to find the magnitude of the gradient vector at the given point and the direction at which it occurs. So we want to also find the direction, which is just the gradient vector itself. Okay, so let's get to that. Now the gradient vector is just in this case, just going to be the partial of x and the partial of y in two separate entries. Okay, that's our equation for the gradient vector. Now, the partial with respect to x of sine xy is just going to be y cosine of xy, and the partial with respect to y is going to be x cosine of xy. Okay, so now we can just plug in our point. Our point is 1, 0. Del f at 1, 0 equals, well, our first entry is just going to be 0 because we know that y is 0. And our second entry is, well, going to be 1 times cosine of 0, which remember we said cosine of 0 is 1. So we just get 0, 1. And this is the direction of the maximum rate of change. Okay, but that's not the whole entire problem, right? The initial the initial problem was asking us to also find the maximum rate of change. So we just have to find the magnitude of the gradient vector. Okay? And remember, I just showed you the whole reason why the maximum rate of change is the magnitude of the gradient vector. If we find the magnitude of the gradient vector, okay, magnitude of this is equal to the magnitude of 0, 1, and there. So it's equal to the square root of the sum of the squares. It's 0 squared plus 1 squared. This is equal to just 1. You can already tell that this has a magnitude of 1 because it's just basically j hat. Okay, so you don't really need to do the whole square root thing if you don't want to. But yeah, that's literally number 8 right there. Okay, that's just finding the gradient vector. Now you may be asked to find the directional derivative, in which case, maybe they give you a direction, you find a unit vector for it, and you use the exact formula that I just showed you here. Okay, so the only other thing you could be asked to do is, like I said, find this directional derivative. Okay, so what they would do is they would give you a direction, excuse me, they would give you a direction, you find a unit vector that's in that direction, so you just normalize the direction that they gave you, dot it with the gradient vector, and there you go, you have your directional derivative. Okay, so actually it's a pretty simple problem if you understand the whole idea of what the gradient vector actually is, what a directional derivative is, and what a partial derivative is. Okay, so on to number 9. All right, number 9, we want to find the local extrema and saddle points of the function. There's a function f of x and y equals x squared plus y to the 4th plus 2xy, and we're going to label each extrema as a max, a min, or a saddle point. Okay, now how do we do the extrema stuff? Like we know how to do that in Calc 1, right? We just we use a bunch of derivatives, but how are we going to do that in 3 dimensions? Well, if you remember, this is going to involve some partial derivatives, okay? And it's going to involve that d, right? It's going to involve seeing if that d thing is greater than 0 or if it's less than 0, and then you're going to have to look at the partial with respect to x, or the double partial derivative or whatever. It's a process, okay? It's definitely a longer process than it was in Calc 1. I'm gonna switch over to the white. Honestly, I don't like the gray as much. I'm not a big fan anymore. I was at the beginning of this video. Now I'm like, nah. Yeah. So I hated max and mins when I was in Calc 3. It was a long process, but don't worry. This isn't as bad as the next problem we're gonna do. The whole idea of this is if you have a point A comma B, okay, it's going to be called a critical point of your function f if all of your partial derivatives, so all of your first partial derivatives equals 0, or if one of them doesn't exist. Okay, so the first step is to find, no, I'm not switching back to that. First step is to find the partial with respect to x. Partial with respect to x of this guy is just going to be 2x plus 2y. And the partial with respect to y is just going to be 4y cubed plus 2x. Okay? If we set these both equal to 0 and we find out what values of x and y are going to make this thing 0, all we have to do is just combine these two equations. Okay, so we get 2x plus 2y equals 4y cubed plus 2x. All right, so the 2x's just end up canceling off, right? There's 2 x's on each side, so these go away. And you're left with, and actually, you're going to have a y cancel off. and this will become a squared. But be careful when you cross off the y's like that, okay? You're going to have y can be 0, right? So y equals 0 is a possible solution to that equation, but when you cancel off the y's, it doesn't seem like it's any longer a solution, okay? So I want to make sure that you get that. And let me show you an example of where that did matter. When you guys were like factoring and stuff and finding zeros, when you were in algebra, if you have like an x times x minus 2 equals 0, you know, you could have just divided that x right over, and you could have just got x minus 2 equals 0, but then you lose one of your zeros, okay? So, you know, one of your zeros is x equals 0, the other is x equals 2. So when we cancel off one of these y's here, okay, we're losing one of our zeros, which is y equals 0. So y equals 0 is the solution, and we also, you know, now end up with this 2 is also going to cancel off actually with this 4, so this becomes a 2. So we have 1 equals 2y squared. So we get y is equal to plus or minus the square root of 1/2. Okay, so if y is equal to the square root of plus or minus 1/2, then what does x have to be? Well, it's kind of pretty easy to see with this equation right here, because basically x just has to be the opposite of whatever y is, okay, to get 0. So if y is this, then x would have to be minus plus the square root of 1/2. Now, if you're not familiar with that whole minus plus notation, like that was something that was introduced to me in Calc 3. But, you know, if you're not comfortable with it, here's what it means. Whenever y is positive, the reason why we have minus plus for x is because x is going to be negative when y is positive. Okay, it has to be. Those two things are bound together, right? So, and whenever y is negative, x has to be positive. So that's why we flip the signs like that. It denotes that x is going to be dependent on the sign of y. Okay, so that's the idea. Now, moving on, what we can do here, since we have our roots, and by the way, when y is equal to 0, x is equal to 0, so we have our 3 extrema, and we can write those down. We have 0, 0. We have rad 1/2, negative rad 1/2. We have negative rad 1/2, and then we have positive rad 1/2. Okay, and just so this doesn't confuse you guys, this is the same thing. I just wrote the same thing. These, you know, the square root of 1 is 1, so I don't know. I just felt like writing it that way. All right, so moving on here. Now we have our extrema, we have to deal with that d thing, okay? And basically the whole idea of d, okay? If you guys remember what the whole d thing was, since we have the extrema, the d is going to tell us what is a max, what's a min, what's a saddle point, okay? And a saddle point just means it's neither a max or a min, okay? So the basic idea of d is that by analyzing all your second derivatives, you can figure out if this, you know, if a certain extrema, so I'll say that instead. If a certain extrema is a max, min, or, you know, neither, if it's a saddle point. Okay? So the formula for d, all right, the formula for d is just going to be a matrix of partial derivatives, of second partial derivatives. So d equals fxx, fyx, fxy, fyy. And when you compute the determinant of this, you get fxx times fyy minus, and you can just write this as fxy squared. Remember, this is just some, this is just all from Clairaut's theorem. Really hope I'm not butchering this guy's name. I don't know, let me know if in the comments if I'm butchering this dude's name. I feel bad, but it's all good. So, and then the rules with this is that if d is greater than 0, and the double x derivative of, I'm going to call this thing a different thing every time. If fxx is greater than 0, it's a min. Okay, so if they're both positive, it's a min. If you have d is greater than 0 and your partial derivative with respect to 2 x's, your second partial derivative with respect to x, I don't know what to call it. This has been like my #1 battle this whole video. I was not ready for that. And if d is less than 0, it's a saddle point. So those are the conditions we have to meet, and you probably already have these in your notes, but I just kind of want to go over that again because this is very important. So let's bring down our partial derivatives, and then we're going to find the second partial derivatives. Okay, and whoa, what am I doing? That was weird. Our second partial derivative with respect to x is just going to be 2. Our second partial derivative with respect to y is going to be just 12y squared. And our partial with respect to x and y is going to be, well, we just go with, this is just going to be 2 again. So, that means that that's also going to be f of yx. But we're going to make our matrix now. 2, 2, that's not 2. That's 12y squared. I put it in the exact wrong place. You guys can tell that I'm getting tired out in my videos, I swear. Alright, so we got 2 times 12y squared, which is 24y squared, and then you have subtraction 4. Okay? And now we have our function for d. Okay? We have our function for d. So now we have to analyze d at each of our extrema. First, we're going to analyze it at 0, 0. At 0, 0, this is just going to be -4, which means that extrema is going to be a saddle point. Okay? D at 1 over rad 2, square root of 1/2, same thing. Negative square root of 1/2 is going to be equal to, well, we just end up this y squared. I mean, it doesn't matter if this is negative or positive, so this is going to be the same for both this extrema and the next, which is this guy. Okay? And basically, that'll just end up being 1/2 when you square it. And so you'll get 8 and 8. So now you have to look at your second partial derivative with respect to x, which is 2, right? Which is greater than 0. So these guys are minimums. All right? So this is a minimum as well. And that's the whole idea. Okay? You can finish this up here. All right? So, all you have to do, you start off by taking those initial partial derivatives, seeing when they're equal to 0, what values of x and y can make them 0, and then you're going to proceed with calculating that d function, okay? And that is just the determinant of second partial derivatives. So you're using those second partial derivatives to analyze whether these things are a max or a min, okay? And that's pretty much exactly how it works for Calc 1, or one of the ways that you can see if it's a max or a min, right? You're analyzing the second derivative, okay? But now you have multiple second derivatives, so that's why there's a matrix of it, okay? That's the gist of it. So now we're going to get into our last problem, and this is going to be a Lagrange multiplier problem, okay? Which everybody loves. This is everybody's favorite topic in Calc 3, aka nobody's favorite. So basically the question here is we need to find the extreme values of f subject to both constraints, and our function is of x, y, and z, and it's yz plus xy, and our two constraints are xy equals 1 and y squared plus z squared equals 1. Now, first off, hold up. What's a Lagrange multiplier problem? Okay? Seriously. I guarantee you that most of you have no idea what Lagrange multipliers are actually doing. And if I said that I knew what Lagrange multipliers were like 2 hours ago, I would be a complete liar. Like, I had no idea what they were actually doing. I just knew how to do them, right? Basically, what Lagrange multipliers are, without getting into too much depth, is they're higher dimensional optimization problems. And let me give you an example of like a way that this could actually be applied in real life, okay? But I can't use this example as an example because you're not going to be able to visualize it because it's in 4D. I could probably talk about like mass density, but that's not something I'm ever going to do because I don't want to. So, and it's confusing. So here's kind of an example right here. An example in 3D would be having 12 meters squared of cardboard. Okay, so you got 12 square meters of cardboard, and you have to find the max volume that you could make with such a box, but it's under a condition. Okay, and that's kind of the whole, this is kind of like the whole Calc 1 optimization stuff. Okay, it's under the condition that the length has to be double the width and quadruple the height. Okay, this is the equivalent to a side function. In this case, we have kind of two of these side functions right here. Okay, so we have two constraints. All right, so these are just optimization problems, and we all know how many people loved optimization in Calc 1. Nobody. So how do you think it's going to go over for Lagrange? Honestly, like sucks. Like, I didn't like doing it, and here I am teaching it. So cool. So the idea now, and kind of getting into the application of this stuff, and so I'm not gonna go into too much depth here at all. Basically, let's say you only have one constraint, and your constraint is a function g, okay, and your regular function is f. Del f and del g are parallel, so the gradients of these two things, of your regular function and your constraint, are going to be parallel at these extreme values that you're looking for, right? You're finding extreme values. So that means that basically del f can be a scalar multiple of del g. Okay, so we put a lambda there to denote that it's a scalar multiple, right? If these things are parallel, they don't have to equal each other. They can just be a scalar multiple of each other, right? Like it's the same thing as saying like a unit vector. Like let's say like 1, 2 is equal to some scalar times 2, 4, right? This one on the right hand side right here is just double the other one. Okay, so these two things are parallel, right? They're both pointing in the same exact direction, but they have different magnitudes, and that can happen. Okay, so when we have two constraints, we can just expand that equation. So what we get is that del f equals lambda del g plus, and our second scalar is going to be mu. Okay, this is what most people use. And we're going to have del h. Okay, and we're going to expand this further so that we can simplify and end up getting our equations. Okay, so expanding this out, we get that the gradient is just, well, the gradient of f is just this, right? Our partial x, partial y, partial z. And that's equal to lambda times the gradient of g, which is just gx, gy, gz okay, plus mu times hx, hy, hz. Okay, so now you can get three equations from that. Okay, you can say that, okay, well, you can do this component-wise in essence. So fx is going to be equal to lambda gx times mu hx. Okay, that's your first equation. So fx equals, I'll do this in gray, fx equals lambda gx plus mu times hx. All right, so that's your first equation. Your second equation is just going to be fy equals lambda gy plus mu hy. Right, so the mu just the scalars are just getting distributed if you haven't already figured that one out. This is equal to just lambda gy plus mu hy. And fz is equal to lambda gz plus mu hz. Okay, so that's how you get your different equations. You just do this thing component-wise, and you're fine. Okay, so we can get our equations for all our we can like actually do out our equations now. So what is our partial with respect to x of f? Well, let's here's what I'm going to do, because I'm not scrolling up every time. I'm just going to bring these guys down. So I'll bring this down right here. Okay, so now we have our different constraints. And what I'm going to do is I'm actually going to break this up a little bit, because we got to figure out what g and h are. Okay, that's maybe something you've been wondering, is what is this? So if this is f, okay, then this guy is g. So g is going to be a function of x, y, and z. It's equal to that, which is also equal to 1. And you may be wondering, okay, well, you're not doing anything with the 1. The 1 will come in later. All right? It will come in later when we actually are doing all the algebra. And there's your function h, like I said, and that one, and the h equation will also come in later. So we're not going to use it for now, but it will come in for useful later. The partial derivative of f with respect to x is just going to be y, and lambda will stay there. The partial derivative of g with respect to x is going to be y, and then we get mu. The partial derivative of h with respect to x is going to be 0. So we can actually just get lambda, or y equals lambda y. And if we divide by both sides by y here, we get that lambda equals 1. Okay? So, and by a quick reminder, lambda cannot be equal to 0. Don't be like one of those people and just put your scalar as 0, because that's not something that works with Lagrange multipliers. Okay, your scalar isn't 0. That'd be trivial, and that wouldn't be meaningful at all. So we're not going to make our scalar 0 here. Okay, and you can research more about that if you're interested in exactly why we can't use 0. But yeah, it just ends up being like a meaningless quantity. Anyways, let's move on to our next part. We have the partial of f with respect to y is just going to be z plus x. And that's going to be equal to lambda times the partial of g with respect to y, which is x, and then we're going to add the partial of y with respect to h. No, sorry, the partial of h with respect to y times mu. So that's going to be mu times 2z. Okay, then we have our last one. So we have the partial of f with respect to z is y. We have that this is equal to the lambda times gz, which is 0. So this lambda will just go away. And then we have mu times hz, which is 2. That'll just be 2z. I apologize. I think I made a mistake. With respect to y, this is not 2z. This is 2y. So now that we've solved these guys, all we have to do now is bring in our two constraint equations from before. And this is where I said that, this one and this one will actually become significant because now we're going to actually use them. So our two constraint equations, we have xy equals 1 and y squared plus z squared equals 1. We're going to use all 5 of these equations. Okay? If you just had lambda, you didn't have an extra constraint equation. You would just have 4 equations. Okay? So, that's something to always remember. It's, the amount of equations that you have depends on how many variables you have. Like in this case, we have a 3-dimensional function. Okay, so we have those 3 variables, x, y, and z, and then we have lambda and mu. So we need 5 equations to solve for 5 variables. But we don't actually need to solve for lambda and mu. We can just find x, y, and z and be done. All right, so let's move on to actually start solving for these guys. And if we want to simplify this guy a little bit, we can just say that z plus x, sorry, that was a little messy. We can say z plus x equals lambda is 1. Okay, we already found that up here, which is just, it's useful. So we can say that this is x plus mu times 2y. Okay, and the x's will just cancel off here. So we get that z is equal to mu, or we can just write this as 2 mu y. Okay, that looks a little nicer that way. Now, if that is the case, then we can, this looks pretty similar to equation 3. So what I'm going to do is I'm actually going to divide these 2 equations and see what we get. If I divide 2 and 3, I get z divided by y equals, the mu goes away and the 2's go away. We get y over z. So what we get is that z squared equals y squared. And I'm not going to solve for z and y, because what I can do is just plug these guys. And this is what you need to watch out for. I have this, and I don't want to make my life harder by just square rooting both sides or anything. So I'm going to use this equation over here, okay? Because I can just plug these in right here and then actually find out what these things are, rather than just kind of beating around the bush and just simplifying more and kind of running into a dead end. Okay, so if z squared equals y squared, then I can just write from equation 5 that y squared plus y squared equals 1. And that gives me that 2y squared equals 1, and I can write that as y squared equals 1/2. Taking the square root of both sides, I get that y is equal to plus or minus rad 1/2. Now this is where you need to be the most careful. Okay, and when I was originally looking at this problem, this is actually where I, struggled a little bit, because the thing about z right now, okay, z squared equals y squared, okay, z squared, it doesn't matter if z is positive or negative, okay, it could be anything. So when y is positive rad 1/2, z can be plus or minus rad 1/2, so it can be, if y is positive, then z can be positive. If y is negative, z can be negative. Or it can be the other way around, because the sign doesn't matter, okay? So if y can be 2 things, z can be 4 things, okay? And, you can do the other way around too. So if you said z could be 2 things, then y could be 4 things, okay? Because it truly doesn't matter what the sign is, okay? So it wouldn't be sufficient enough to say that z is plus or minus 1/2, because if you did, then if y is positive, then you're saying z has to be positive. Okay, that's not the case. Z can also be negative when y is positive. So you have to have actually 4 cases of z to compensate for this. Okay, and that's just kind of the limits of when you have multiple plus or minuses in your solutions. That's the actions that you have to take. So that's y, that's z, and we also need to find x. Well, we have that xy equals 1. Okay, so if xy equals 1, we use equation 4, and we get that x times plus or minus rad 1/2 equals 1. And if you divide by the square root of the plus or minus square root of 1/2 on each side, you get that x is equal to plus or minus rad 2. Okay? So now you have your x, y, and z. So you're going to have 4 different extrema to work out with. Okay? Remember what our original problem was asking for. We're finding the extreme value. So we're finding the extrema of f. Okay, and we want to actually find the value, so we can't just like write the coordinates and call it good. We have to actually find the maximum, or sorry, find the values of f. Okay, that's what it means by extrema, right? So if we find f at our first one, so let's say x is rad 2, we'll say y is the square root of 1/2, and we'll say that z is the square root of 1/2. What we'll get, and remember what f is, I'll bring that down. So we have it. Oh, I skipped. Okay, f is right there. So we have y, which is square root of 1/2, times z, which is square root of 1/2, plus rad 2 times 1 over rad 2. Okay? And it's actually nicer to write this as 1 over rad 2 rather than rad 1/2. So, it just is less to worry about. And you can see easily that the rad 2's cancel off here, and you end up with 1. So rad 1/2 times rad 1/2 is 1/2. Then you have plus 1, so you get 3 halves here. So next is going to be rad 2, rad 1/2, and then we'll do when z is negative. So we'll write it. I need to be more consistent with the notation. So let's just do like that. Okay. So this is going to be equal to y, which is 1 over rad 2, times z, which is negative 1 over rad 2, plus x is rad 2, and y is 1 over rad 2. You get that this is equal to, we have a negative 1/2 plus 1, that gives you 1/2. So already you have multiple extrema. Now, if you keep going here, you get rad 2. Oh, sorry, you can do negative rad 2 now. Negative 1 over rad 2 and 1 over rad 2 to get y times z is going to be negative 1/2 plus xy is just going to be 1, and you get 1/2 again. And lastly, if you did all these things as negative, you get, remember, yz plus xy. So we have a 1/2 here, and then we'll get a plus 1 here, and we'll have a 3 halves. So our two values are going to be 3 halves and 1/2. So you can see here that then 1/2 will be a minimum because it's smaller than 3 halves. So this guy will be a maximum, and that's it. Okay, so Lagrange multipliers are and I'm going to go over this whole thing real quick just because Lagrange multipliers are a tough topic because it's so lengthy. It's kind of like partial fraction decomp because it's a lot of algebra, So this is basically, a higher dimensional optimization problem. Okay, I gave you an example of kind of what Lagrange multipliers can be useful for. Okay, we talked about how we set up the Lagrange multiplier equation, and we start out getting our first 3 equations from this big thing. All right, we use our constraints with our 5 equations, and then we're just solving for x, all the values of x, y, and z. Okay, we found those. So we found, not here, we found y, we found z, we found x, and then we just found the actual values of the extrema, right? So let's say that this function was what do we have? So this is, yeah, this function. So let's say that this function of x, y, and z is w. So we found that w is 3/2 and w is 1/2. That's its max and the min. Okay, so that's the whole idea of Lagrange multipliers. So it starts off with algebra, and it starts off with a little bit of partial derivatives, and it ends with some algebra, and that's really it. Okay, so really lengthy, but honestly not the hardest thing in the world. All right, so that's going to do it for part 1 of our Calc 3 final review. Next time we're going to be going over, in the next video we'll be going over some double integrals, triple integrals, and then we'll be going over change of variables as well. That'll kind of cover the multiple integral section. And then for vector calculus, we're going to be touching on line integrals. We'll be doing, Green's theorem, Stokes' theorem, divergence theorem. We'll be doing divergence and curl, surface integrals, all that stuff. So we'll really hit it home with vector calculus, because like I said, that's going to be a big part, I think, of your final, especially, and listen, you got to know that your final is going to have at least one Lagrange multipliers problem, at least one max and mins problem, and probably a gradient and directional derivative problem as well. So 8, 9, and 10, those problems that we did are going to be very crucial for your final. The other stuff may get asked, but I think the 8, 9, and 10 have the highest probability of actually getting asked on your final. Okay, and all the other stuff is definitely fair game that we're going to be talking about in the next video as well. Okay, so I'll link that video on the end screen here, and you can go over there and check that out when you're ready. I think you should take a break before. Don't try to cram this all in one night. Okay, make sure that you're studying smart. But anyways, yeah, subscribe for more content, and if there's anybody that you feel could use some of this Calc 3 final review, definitely share this video, and it would really mean a lot to me. Thanks so much, and I'll see you soon.